My gosh, something went wrong. What happened to why isn't my camera working? Oh, I have to press a button on the camera itself. Okay, what about now? Yeah, there it is. How's it going, YouTube? What's up? We're back. Another day practicing mathematics. Let's also go live on Twitch as well. Almost forgot. What's up, y'all? How's it going? I hope you're having a great day. This is gonna be fun, dude. Brand new series, practicing fundamentals, basic mathematics. So we're going to get started on this new book. We're reconfiguring the stream a bit. We just finished a cycle doing 4 representation theory streams in a row. First we did 4 calculus, then 10 linear algebra, and then 4 representation theory. And as I've talked about many times on this stream, that follows a structure that means high school math, college math, and then graduate level math. I realized, it's kind of pretentious to call calculus high school math. Like, I did learn calculus in high school, but calculus is a college level class. Calculus is something that, like, especially to the level of depth that I want to do calculus in, it's definitely a college level class. Even if it is also offered as like the last high school class. Hey, what's up, Holmes? What's up, Ethan? How's it going, y'all? Dude, I'm excited about this. I think that it's going to be better to start from the ground up, and let's do actually high school math from the beginning, from the, very, very beginning. Let's do some high school math. This is middle school, high school math, but it's middle school, high school math done right in some sense. Like, this is literally proof-oriented, beautiful math. So not only do I want to kick off this series, I'm also announcing today something I'm excited about. I'm going to offer a course, y'all. So it's going to be free. It's totally free. I'm going to film proper lectures on basic mathematics, like following a freaking syllabus and everything. So I have an idea for the first lecture that I'm going to film live. So there will still be the live practice sessions like this, and it'll be fairly unstructured, but then in some portions of these streams, sometimes I'm just going to film a lecture live, and then the plan is to clip it and upload it as its own separate individual video. So, dude, I'm excited for this, y'all. I'm excited. Do I know about the JE exam? I do. What's up, Ritika? How's it going? Yeah, the JE exam, as I understand it, is not the kind of math that I like to study. I like proof-based, conceptual, theoretical mathematics. And from what people have said in the chat, it's a lot of hard computations rather than proofs. Is that accurate? Ritika, nice to meet you. What's up? So, today we're going to be doing an introduction to pure mathematics. And I've had this theory for a little while that somebody could teach intro to proofs in high school. And truly, in high school, teach intro to proofs with familiar math. Like, you don't have to, like, my college taught intro to proofs with abstract algebra, and it really was a course for math majors. Like, unless you were a math major or a math education major, you wouldn't take intro to proofs with abstract algebra. I think that somebody can teach intro to proofs with regular algebra, and you can call it intro to proofs too. So I'm imagining a course that is either an honors middle school, honors high school courses taught out of this pure math book, or also, I mentioned a course, math for adults as a hobby for fun. Like, So I'm very excited about this. We're going to be kicking off the Math Hobby Academy or something like that. So there will be, filmed, prepared lecture videos, which I film live, and then I'll do some light editing and upload it as its own separate video. Cut out these ums and annoying things like that, and just do some light video editing. But the goal is still to film these things in a one-take performance, because that is practice for me, because I want to teach this stuff in an actual live classroom. And you can't cheat with video editing in an actual live classroom, right? So, dude, I'm excited for this. So today we will be filming our first lecture. And anybody who wants to join, we will start offering also Saturday group lessons. So there will be a Zoom session. It won't be filmed. It won't be recorded. It'll be a hangout session, which is based on this book. And it'll be a reading group for this book, for adults studying math for fun as a hobby. That's the idea. If somebody is already part of my classical guitar academy, you also get free admission to the math academy for fun. Or just, buy one, get one free is what I'm saying. So, heck yeah. Let's get started. But that's a separate thing. We will be uploading my practice sessions, my filmed, practiced lectures, as its own video series. Okay, so are you going to make us practice first? Yeah, you should be practicing. Absolutely. I'm practicing. You should be practicing too. If anybody is new, if anybody's watching the VOD of this, first off, hello. If you're still watching, thank you for watching. Please consider hitting the like button if you like this so far. Secondly, nice to meet you. My name is John. I am a passionate enthusiast in mathematics. I graduated with a degree in pure mathematics in 2012. Then I worked in the software industry, working at Apple and Google and a few other companies as an iOS engineer. So now AI is making software a lot less fun. I just don't enjoy writing. You listen to me, I guess. I am professionally trained in math. I trained to become a research mathematician, and then I worked at some of these fancy companies, which are really hard to get into. You have to be quite good at math, honestly, to get into companies like Google. Okay, so today we're going to begin chapter 1, literally on numbers. Dude, this is going to be fun. So we will be loosely following this book. I'm not going to strictly be following it. I'm not just going to be reading this book and writing down every single example that Lang uses. I'm also going to be pulling ideas from other books and other topics of math that I know. And the point here is somebody who just wants to study math as an art form in itself without any deadlines, anything like that. All right, so section 1.1, we have the integers. Somebody asked, what is the table of contents for this book? I believe that today we will be doing section 1.1 on the integers, and we will also be doing rules for addition. And this is the material that we'll be covering today. After that, just so that you have an idea of what is in this book, rules for multiplication. Section 1.4, even and odd integers. And divisibility. So all of this sounds super easy, right? But if you are an adult and you're interested in picking up math as a hobby, you'd be surprised. Like higher math classes, I had math classes like number theory or something, which started literally like the syllabus looked quite similar, even though it was an upper division class. Mathematics is not just matching patterns and doing computation. Like real mathematics, pure mathematics is about proving why those patterns work in the first place. It's about the concepts of math. So we will be actually working proofs about the integers, addition, multiplication, etc. So rational numbers. And then in section 6, we have multiplicative inverses. Somebody asked how many sessions we'll do on this book. I have no idea until we're done with it, I suppose. Yeah, like I want to be practicing teaching middle school and high school math, and the idea is like an honors course for middle school, probably. Yeah, Lockheed is going to be dropping in the universal property of natural numbers. Yeah, we're gonna, like, when we're working with the basics like this is some mathematicians, pure mathematicians who are researchers, they spend all of their time in like the basics, in the fundamentals and foundational math. So, I mean, it would kind of be a stretch, but I could try to fit in like logic, like a logic course into a fundamentals series. I think that's, I mean, definitely we'll get the basics of logic just for proof strategies and such. But, I mean like logic, like, you know what I mean by that, Lockheed. It's really basic. Yeah, how many episodes are we going to do? Oh, yeah, I forgot to say, I'm reconfiguring the stream a bit. For a while, here's the old structure. Especially since you're new. I don't think I did this yesterday. For a long time, I was doing linear algebra. Right? And I kept resetting. So I would do one stream on chapter 1, then I'd reset, I'd do another stream on chapter 1, and then I'd do a stream on chapter 2, and then I'd reset, and I'd do a stream on chapter 1, 2, 3, and then I'd reset, and then we do 10 streams in a row. After that, after we started, this is the entire book, it's 10 chapters. After that, I started adding calculus. And I would do one stream on calculus. And then I'd do 10 streams in linear algebra. And then I would do one stream in representation theory. The idea here is that red is high school, green is college, and then yellow is graduate school, right? Then this changed to 2 streams in calculus. Maybe this looks better if I keep linear algebra in the middle. It's a little tricky, but we do 1 stream in calculus, 10 streams in linear algebra, 1 stream in representation theory. You see what I mean? 10 streams in linear algebra, and then 2 streams in representation theory. We kept doing this. And then the cycle that we just finished was 4 streams in calculus, 10 streams in linear algebra, and we just finished a 4th stream in representation theory. So this is an announcement to those who are live that I'm changing changing the structure. Let's not be lazy. We're only missing one line in between these two, right? So, I mean, mathematicians will put some dots just to omit one line, won't they? That is a thing that we'll do, but so okay. So this was a structure that we're doing. So, we could probably prove some freaking closed form identities about this using something called the triangle numbers and things like that. But in any case, just for one example, notice that here, this was 18 streams. And then the next one would have been 20 stream cycles, etc. I'm rebuilding right now, and we're going to go to a new structure. This is the old structure, and it was, once again, college or undergraduate math, graduate level math, and high school. Okay. So this was the old structure. Now we're going to do something similar but different. Now we would reset and do 5 streams of high school, 10 of linear algebra, 5 of representation theory. This time I'm going to do 5 of each. So it'll be high school, or maybe even better, I call it secondary school. Because I want to be including middle school into this, I realized. Secondary, college, and then graduate level. This is the new structure, and it's going to be 5 streams of basic mathematics, 5 streams of calculus, and then 5 streams of representation theory. So we are, by popular demand, we are retiring Fraleigh as like a primary character or a primary book of the stream. Something that I like about this is that these are going to be weekdays. So now I'm only committing to Monday through Friday streams on weekdays, and then I have special events or special streams sometimes on the weekend, but we won't be always working through the weekend. So then, in other words, we have 1 week of middle school, high school, 1 week college level, and then 1 week graduate level. And then we just keep looping. We'll just keep things simple now. Like, we're not going to keep increasing the lengths anymore, like I used to. Okay, so let's see. Let's read chat. How's it going? Oh, your desk looks a lot like a cat. Was she in front of the camera at some point? Yeah, heck yeah. Oh, I suppose if we're starting with integers, then I should drop the universal property of integers. How should someone manage math while doing a computer science degree, bro? Just a little bit at a time, man. Like, track it and just, 15 minutes, 30 minutes. Treat math like a hobby, dude. Treat math like a hobby. Like, keep it as a hobby. Don't try to make money from math. There's no money to be made in math. But just like as if you wanted to keep... I lost my pen. Where did it go? Just, think of, if you wanted to keep practicing the classical guitar in college, what would you do? If you wanted to continue learning a musical instrument in college, what would you do? You time box it, and you strictly only let yourself do 30 minutes a day, but you still keep practicing every day. Like, that is really key, in my opinion. If you want to, just maintain your hobbies, dude. Don't let, like, work or college or your education, like, don't let that get in the way of pursuing fulfilling, deep hobbies in your life. Like, that's a message I would just want to put out there and just emphasize. And, it's not a zero-sum game. If you develop deep hobbies that you're proud of, like classical guitar or mathematics or other things like that, I think it makes you better at your day job. I think it will recharge you and make you better at studying computer science. Like, even if you don't need pure math for computer science directly, like, dude, indirectly, obviously pure math is super useful for computer science. So keep studying something like abstract algebra or fundamentals, even though you don't have courses on it, it's going to help you when you do data structures and algorithms or other things. And it's just a better hobby for your brain than scrolling TikTok, dude. And like, most people, while they're doing a bachelor's degree in computer science, they're fucking scrolling TikTok or watching Netflix as a hobby. Just drop that, drop the brain rot, and continue practicing mathematics or the classical guitar or something that recharges you and makes you better at your day job and feeling more fulfilled. I don't truly have anything inherently against social media. I'm obviously on social media right now, and there's things to love about social media, but if you're just scrolling and just consuming, like, I think that that's objectively a worse hobby than chess or cooking or math or classical music. So that's a lot to answer your question. Ooh, somebody got a 5 on pre-calc. Slayer, let's go, dude. AP pre-calc? You took the AP exam in pre-calc? I was tutoring somebody for AP pre-calc. That's awesome. Congrats. You actually helped me out, bro. No way, dude. That's awesome. Are you serious? Bro, Slayer, the GOAT, dude. I'm going to freaking print that out and put that on my wall or something. One day we will start a series on category theory. I do think that will happen at some point. Yeah. Another thing is maybe the books alternate, in college. I don't have to commit to always doing calculus. Maybe we'll continue linear algebra, or maybe we'll do number theory some weeks. Just appropriately, like, without, like, getting distracted by shiny new things. Like, oh, I want to start learning category theory this week, or something. Like, if it were category theory, it would be under the graduate level list, right? Like, I would love to study category theory, or even for me, Galois theory. Like, dude, I want to learn all these things, but I want to stay focused so that I'm productive and making progress. But yeah, at some point, I think we'll start alternating the subjects themselves as well. I don't know. We're figuring this out as we go. As you do these math questions, it's going to be interesting to hear how someone who is good in math thinks through math problems. That's part of the idea. Like, you'll see me totally working. I did it a lot yesterday. I was truly learning new math for the first time live and thinking through how to solve those problems. Hey, what's up on Twitch? Dragon so hype. E to the pi I plus 1 equals 0. Bro, that is actually, in my opinion, one of the most beautiful facts in math. E to the pi I plus 1 equals 0. I even had this framed on my wall at one point. I had like a little painting, actually, like E to the pi I plus 1 equals 0. I do think that this is an incredibly beautiful math fact that a lot of people never see in high school, and it's a shame because it is really, really pretty. Yeah. Nice to meet you, Dragon. I'm also on YouTube. Unfortunately, I haven't figured out how to get chat interleaved yet, but feel free to watch wherever you prefer. Nice to meet you. Okay, people are talking about category theory on YouTube. Stocks and sheaves. I'm not even gonna read that. You can find this in somebody's thesis. It's really nice. Okay. Oh, that's the modality application thing that you're talking about. Let's see if I can stay long enough in the stream to see one number other than 1, 2, 3 in this stream before I have to go. Yeah, I've been yapping. I've just been yapping so much. Well, you just saw E and pi just now. There you go. No money in math. Every mathematician in shambles right now, basically. Dude, low key, imagine if you were the reason why I'm taking a math minor in Harvard with econ as my major. Dude, I'm officially an influencer. Like a micro, tiny, mini, nano influencer, but I am officially an influencer. Okay, because I'm officially a math influencer, in fact, because there was one viewer who was going to retake Calculus 2, even though they got a 5 on the AP exam. And I said, no, dude, that's stupid. Don't do that. If you pass the AP exam and you can get college credit, screw that. Take linear algebra, even though it wasn't required for his degree. Of course, I am a linear algebra goblin, and I just want everybody in the world to learn a little bit of linear algebra. So I convinced them not to retake Calc 2 and instead to take linear algebra. And now somebody else just said that you helped me pass with AP Pre-Calc. Dude, I'm officially a micro influencer. That's awesome. And now, just for completeness here, this dude says that they're gonna add a math minor at Harvard. That's amazing. That's cool. All right, it's on the iPad, so now it's official. You have to do it. Is I a number? Yeah. What counts as a number? Don't get too philosophical. Like, that's the danger of studying fundamentals. I think I'm starting to simultaneously do formal coursework / research. It's self-study, pure math. I thought only one was possible. Yeah, nice, dude, nice. Okay, one must watch a cat clean itself today. All right, I'm caught up on chat. Let's go. All right, so these are the sections. So let's hang out. Let's chill. I'm going to do a practice session first before I do the lecture. So I just want to read just a little bit from this book and see what we have. I mean, I should also, if y'all are curious, I could write out the whole table of contents for the other chapters. But you can find this PDF online. It's not hard to find. I say matrices are numbers. Yeah, I tell students that. I'm like, in math, we learn math facts about numbers, but in higher math, we start extending that to studying objects. You can just call those numbers too. Like, you just start working with weirder, different numbers. But really, we're studying mathematical objects and some of them satisfy and behave very similar to regular numbers. Yeah, I mean, I say that matrices are numbers. Hey, what's up, Chandan Gaming? How's it going? We are working through loosely following Basic Mathematics by Lang. So find this book, go get it, go buy it. It's totally worth it. I don't even have an affiliate link set up yet, but what's your review? So far, it's really nice. Like, so far, I think that this book is super nice. Tony Stark, what a name. It's a pure math book for high school math, for fundamentals, for like quote unquote basic math, which is a little demeaning. This guy is a little demeaning sometimes as an author. I took his graduate level algebra book, or I audited a course based on his graduate level algebra book, and sometimes you feel like an idiot, and I think that his intentions are good, but yeah, Tony Stark. Is this book about pre-calculus? Yeah, pre-calc. It's all pre-calc. In the sense of, here, do I have the PDF loaded? I do. Look at that. Okay, I fair use. This is all fair use. Fair use. I think it's fair use. Here is the table of contents, y'all. Part 1, Algebra. I don't know why this PDF doesn't dark mode, but this is Chapter 1 on numbers. Then Chapter 2 on linear equations. Chapter 3, real numbers. Chapter 4, quadratic equations. An interlude on logic and math expressions. And then Part 2, intuitive geometry. Distance and angles. Chapter 6, isometries. Chapter 7, area and applications. Part 3, coordinate geometry. Coordinates and geometry, operations on points, segments, rays, and lines, trigonometry, some analytic geometry. And then Part 4, miscellaneous, he calls it. Functions, mappings, complex numbers, induction, and summations. Dude, I wasn't even sure if he was going to do induction. I'm glad that he does. And then determinants. So this is all pre-calculus. All of it is pre-calc. Do you think we're going to get through this in a month? No, definitely not. We're going to be doing this for a long time. And we're going to be doing it in depth. We're not just going to be like speed running this book. Like, we're going to be running this like a lecture, like a course. Yeah. I think Tony Stark, yeah, you could totally do Calc 1 after this book. Yeah. Yeah, you're going to be here every day. Heck yeah. Heck yeah, dude. I'm happy to hear that. So, one thing that is lovely, I think he's got a great point here. I love this part in the book. What's a nice high contrast? I hope to induce teachers to leave well enough alone and to avoid torturing a topic to death. I love that. It is easier to advance in one topic by going ahead with the more elementary parts of another topic. Dude, I think that this is how I've been working on this stream, and I think it's a great idea, where the first one is applied. The brain much prefers to work that way rather than to concentrate on ugly technical formulas, which are obviously unrelated to anything except artificial drilling. Dude, this is what the U.S. freaking math education system emphasizes. Just artificial drilling and going depth first. Some rote drilling is necessary, yeah, but how do you strike a balance? So, yeah, just the idea is that we can go forward, come back, bounce around the book. We don't have to be doing every section one at a time, which I think is excellent. Yeah, Yeah, there's some other comments about this, but in any case, yeah, I think that this is a really great book, and I hope you all get it. Let us go ahead with the elementary parts of category theory. Nope, not today. No. All right. Since this is the practice stream and it's a live session, I haven't worked any of these problems yet. Let's work a couple of problems before I run my lecture. I think I have an idea in mind for what the lecture is. But in the practice streams, in these live streams, I want to be primarily problem focused. So before I run a lecture, I want to make sure I can do these exercises. Number 1, express each of the following in the form 2 to the m, 3 to the n, a to the r, b to the s, where m, n, r, and s are positive integers. Dude, this is the first problem in this like middle school, high school book. I think that this is great. Okay, so first, 8a squared b cubed times 27 a to the 4th 2 to the 5th ab. Let's work this. This is not the worst way to spend your time. If you are an adult who felt like you never learned math the right way or something, or that you never really understood or got math, it might be because your course was not conceptual enough. I really think that getting theory helps some people understand math, like why do these patterns work and things like that. So how do I solve this problem? What we are going to be using, let's do a solution for each one of these individually. I like my accent color underlines. Okay, so we use the fact that a times b equals b times a, right? Which is called commutativity of multiplication, okay? So this is already in section 3 or something. I don't think it's a bad first exercise. I think this is a good first exercise. I think that this is a cool first exercise. So 8a squared b cubed. Let's work in parts. Well, actually, we need a little more. Let's see. First, yeah, like if we're, okay, we're going to use a few different facts. We're going to need also this fact. If you can't name this, you need to be able to name what this property is. And we use it all the time because we just kind of learn that it works. But this is an important property. This is not called the distributive property. This is called associativity. Of multiplication. What order do I want to do all this stuff? So this times 27 a to the 4th times 2 to the 5th ab is equal. So when you have multiplication on the right, with a parentheses, we can regroup this as 8a squared b cubed times 27. And if I were like even more formal, I don't know how far, like if we want to do it one step at a time, if I were teaching a course on this, would I do every single individual rewrite the way that you do in Lean? With like, I'm imagining if I were to prove this using Lean without the simplify function, it would be somewhat tedious and it would take multiple rewrites. So if we repeatedly apply associativity and commutativity, then we ultimately get to rearrange these terms so that we have all of the constants multiplied together times all of the a terms multiplied together times all of the b terms multiplied together. So I could say by repeatedly applying these two facts, then we ultimately get to regroup and rearrange the multiplications. It's a little tedious to do every single step in this rewrite, but like this would be a double bracket. And then I think that then we would have this other bracket times 2 to the 5th AB. This is kind of super tedious, but I think that that would be the regrouping. Or we could use commutativity once and then rewrite. So right now I'm not lecturing. Let me really re-emphasize that. Right now I am just trying to think how I would explain this in a solution set. Like I'm actually working this together with you all. I want to at least show one application of I want to show at least one application of this fact. So using commutativity in the middle term, we can get this. So in a math proof, we should justify every single step. Commutativity. So what I did was I swapped these two. And now let's do one more. So here I regrouped the parentheses by associativity. Okay. So I regrouped these yellow highlighted parentheses. Where now we have 27 times 2 to the 5th times AB. I think that this, I don't know if that last parentheses is needed if it were lean. Like, the level of formalism that you get used to when you start working with something like lean really makes you think about every single individual step and where the parentheses are applied. But now I've shown one example of commutativity. I swapped the 27 and a to the 4th. And then I showed one example of rebalancing the parentheses so that I regroup the parentheses now to 27 times 2 to the 5th, a to the 4th on the left, ab on the right. So y'all might be getting annoyed with me at like how formal I'm being right now, but it's worth it. Like, what is this selection thing? Okay. So ultimately we regroup these, and then next we apply prime factorization, maybe, or factoring or division. Let's think of that. So 8 is 2 times 4. Let's do one application to both of these terms. 27 is 3 times 9. And then 2 to the 5th, I'll leave as it is. The rest remains as is. Continue applying prime factorization. And then we get 8 is 2 cubed. And then 27 is 3 times 3 times 3. Do I want to 3 times 3 times 3 times 2 to the 5th we do another application of commutativity in this first term. I'm being annoyingly strict about not simplifying these last factors because I want every step to be justified by just one math fact. Commutativity in this step, and then here we were factoring or applying division. All of this was factoring composite numbers into primes. And now we're going to use the definition of exponents, which gets us the fact that a to the b times a to the c is a to b plus c. This is a math fact that we need to prove in the section, in the theory, but this is a result from the definition of exponents. Eventually gets us this math theorem or result. But we're just working on an exercise for now. Okay, 2 to the 8th times 3 cubed times... Now I can, again, apply this fact about exponents, that if the base is the same, then you add the powers. So this is a to the 7th, and now this is b to the 4th. At this point, parentheses around a single element don't do anything. Parentheses around a single number, like there is no operation, no multiplication operation or something. So now we have that, and now we can omit parentheses by multiplication associativity. Associativity of multiplication means that the parentheses are, in some sense, optional. If you have 3 or more multiplications, that is. If it's just a series of multiplications in a row, you don't need to write parentheses. So this is like a math fact. Whether it needs to be an axiom or a definition or a theorem, not exactly sure, but now this is finally in the form that this exercise asked for. So this simplifies to this. So let's box there. Maybe I give myself like a little equals ... equals that. Okay, so I was very formal. It is a theorem for integers. I assumed it would be, or I was thinking that it would be. Let me see. So you can literally just put the variables together. Not sure which part. I'd have to rewind and see exactly what you all were writing. Are you going to ask us questions too? I might. I mean, I could if you all want. Gets you thinking about uniqueness of prime factorization. Yeah, absolutely. One could try to think about why the answers to this exercise may be unique. Associativity is something everyone uses, but no one states. Yeah. So, Lockheed, you suggested that we could introduce something like the octonions. Nice. I didn't realize that the octonions are non-associative. I love the idea of finding more non-associative examples because I do really like this idea, and I want it to be part of my course. Is like when I introduce multiplication and the commutativity of multiplication, I also introduce multiplication of matrices, and now we have one example that is commutative and one example that is not commutative. Like I want to be teaching the little children linear algebra. Like that's how much of a linear algebra goblin I am, you know? Yeah, Arad, I'd put this under one of those things you should see once in your life and never again. Exactly. I mean, me too. I think that you should do all of these tedious steps once in your life. Like, I don't know, maybe even doing every single individual rewrite in these ... steps where I'm saying I just do this multiple times in a row, and then eventually we keep rewriting this until it's in this form. And it takes like 20 steps or something. But now that we've done one of them, at least the general sketch of it, now let's just frickin' do it for part B. 16b cubed a squared 6ab to the fourth times ab quantity cubed. Okay. So I'm just going to immediately say that this is... Okay, so 16 is 2 to the fourth. If I collect all these... So 16 is 2 to the fourth. 6 is 2 times 3. Then I can see that the constants multiply to 2 to the fourth, 2 to the fifth times 3. He did say that we want to write all of these exponents, so I'll do it. I didn't use the colors I wanted. I'm sorry for being so picky about this. But 2 to the fifth times 3 to the first power. Now, how many A's are there in total? There's 2 from this first term. 2 A's. There's 1 from this. And then there will be 3 from this term. I think that this one is worth maybe an intermediate line, but as we keep getting better at these, we would be able to see that immediately. And I'll think about in my solution set whether I want to how many lines I would want to show in this presentation of the solution. What I'm thinking about is, do I want to, I kind of want to write this as a cubed b to the fourth times ab. I feel like we could show one step like this, or immediately apply the power rule for, or the power of a product rule. The power of a product is the product of powers. I think is, so we're implicitly using a few different facts. AB equals BA. We're using associativity again. And we're using another fact. AB to the C is A to the C, B to the C. I don't know if I should start using N to assume that that's a natural number, but I think that this is fine. So I use all of those facts in that second line, and now in the third line, we use commutativity, and we collect all our A terms, A to the sixth, B to the seventh. I think that the dot is implicit and clear enough if you have exponents. So there we go. There's our solution. 2 to the fifth. I'm sure I will make little arithmetic errors left and right all the time in this, but part C. I'll let you all work these if you want to. 3 squared, 2ab cubed, 16 a squared b to the fifth, 24 b squared a. Part D. So these are, it's just going to be the same thing and some practice. But aren't these cool first exercises for a middle school book? Like, I mean, they're kind of, they're kind of hardcore, I feel, to jump right to this. And, like, you kind of have to very quickly get used to some of these math properties that I don't know. I see high schoolers who struggle with a lot of these really fundamental commutativity and associativity facts. Like I see students who are weak in their fundamentals who would struggle with these. And a lot of people would be able to write down the correct solution, but they wouldn't be able to explain why it's correct. I think most people, honestly, most high schoolers would be able to simplify. In other words, like most high school problem sets will just say simplify this. And that's a little vague. Like, what does simplify mean? Is this simpler than the other? I don't know, dude. Like, I liked the larger numbers, not primes. Like, why am I blinking? 32, 64, 128, 256. I mean, is this simpler? you know? Or, like, which of these is simpler? 256 times 27 is 69, 12, a to the 7th, b to the 4th. Which of these is simpler? Like, it's honestly kind of a philosophical question. There's no right answer. It depends on the context. Like, a lot of the time that we're working in math, it's really nice to see the prime factors, because if we have maybe a division of freaking 2 to the 8th, 3 cubed divided by 2 to the 5th times 3 times 5 or something, this is so much simpler to work with because we can use properties about division and powers. So we could quickly say that this is 2 cubed times 3 squared times 5 inverse or something. So keeping numbers factored into their unique prime factorization often is simpler, but this is just a single number. So which one is simpler? Like, the term simplify in high school math problem sets is vague, whereas this problem is very concrete. It says express in this form, right? Yeah, 2 to the m, m is 8, n is 3, r is 7, s is 4, or something. Would even be another way to answer the question. All right, I'm kind of getting a little off track, sort of, or like a little too in the weeds, maybe. Okay, so answering and justifying the steps why you can simplify that first form into the second is necessary. Like, it's not just about getting the right answer, it's about the reasons why and the steps in between. Yeah, would it be easier to hand wave that you could continuously cycle a factor from the right to the left by repeated commutativity? That's a good point, yeah. Associativity is an especially annoying one to write down the individual steps of, yes, because when you're applying one associativity, sometimes you have to introduce new parentheses, and then suddenly you have like 4 parentheses, nested parentheses. Associativity can be really tricky to show the individual steps on. And yeah, I also noticed that, yes, I was already implicitly using associativity, like these original. Yeah, I mean, well, no. Yeah, in this term, in parentheses, there's 3 terms. So there's already a usage of implicit associativity. Although, I mean, as long as you define that if there's no parentheses, it's the first one times the product of the other two. We're like a little off track. I know, I agree with your point there. That is, I was using a little bit of hand waving on associativity. Lie bracket is the most standard example for a non-associative operation. Ooh, yeah, I would not be able to introduce Lie bracket. I don't even know what a Lie bracket is for myself. I would not be able to teach high schoolers about Lie brackets, I don't think. The cross product, that's a good one. But that requires some machinery, you know. Hey, take care, man. What's up, Lockheed? Or yeah, mix up. Yeah, I think I missed you, but thanks for stopping by. Great to see you. Enjoy whatever you're gonna do. Is that a pure maths book? Yeah, kinda. I mean, it is definitely written by a pure mathematician. It is like literally like one of the freaking gods of pure math books is Serge Lang, and he wrote a lot of excellent pure math books. And this is his high school math book. So it is a high school math book, middle school, high school math book, written by a mathematician, like quote unquote real math, like proof oriented high school math, which is pretty awesome, I think. Okay, so yeah, that's the very first exercise. Let's take a look at the next one. Right now, I'm just chilling and practicing. This is not my lecture. I will be filming a lecture either live or on my own, but I'm thinking about which exercises I would want to assign. So I'm beginning a course. I'm beginning a course which includes group calls, group Zoom hangout, problem solving, open, group lessons on Saturdays on this book, and free public YouTube lectures. Okay, we've got a proof. The word prove showed up, and that's how you know that this is a pure math book, which is excellent. So we've got two different facts that we want to prove in this exercise. So, solution. Oh, yeah. Since this use the word prove, so I get to use the nice word proof for this solution. First, a plus b cubed is by definition a plus b times a plus b squared. Or I could say by definition it's a plus b times a plus b times a plus b. And this is a plus b times a plus b squared. And this is, by distributivity, a times a plus b squared plus b times a plus b squared. And now, the book, I believe, has already shown... The book has already, at this point, proven... Or not? Does it not? That's kind of hardcore, I feel. Oh, wait. Oh, I was jumping to the wrong exercise set. I was thinking, dude, these are a lot of multiplication exercises right now. Like, did we just skip all the addition exercises? Okay. Well, that explains it. Okay. So this is a practice stream. Okay, yes. So in the text, we do have this fact that a plus b quantity squared is a squared plus 2ab plus b squared. Now we can apply distributivity distributivity and commutativity let's show the regrouping. A squared b is here and here. And a b squared is here and here. And the final term is b cubed. Okay. Now, to write out the proof and justify all the steps, I spoke them out loud. We could write the properties in every step. Like this is like the definition of powers, of integer powers. This is, again, the definition of exponents, of integer exponents. This is distributivity. Here, oh wait, yeah. This was a theorem in the book. This next line was distributivity again. This next line is commutativity of addition, commutativity and associativity, but and then the final line is you can think of it as distribution and then addition, or yeah. How do you justify that last step? So if you factor out a squared b, and then you add 2 plus 1, then you get 3. That's like a little extra formal, but yeah. This looks like ketchup and mustard. What's up, the real deal? How's it going? I'm practicing right now. Don't think, if anybody watches this VOD, don't think that this is exactly how I would run a middle school classroom, because this is a little more in the weeds, I feel, than a middle schooler would be ready for. But an adult might enjoy this. And I would be checking in with the adult and what they're interested in and what they're not. Like, if they get kind of excited about like showing all these little micro steps, then that's great. Like, let's focus on that and get really formal. But if they're not really motivated by it, we can do some hand waving or skip some steps. I don't know. Proofs are somewhat of an art form. There's a subjective nature to proofs where the author needs to decide how many details are worth filling in. Because it becomes very tedious to write out the justification for every single step. Similarly, a minus b cubed is a minus b times a minus b squared is a times let's keep it. A minus b squared minus b times a minus b squared. In the book, in the section, they've proven that this is a squared minus 2ab plus b squared minus distributing through the minus b times a squared minus 2ab plus b squared. Distributing a cubed minus 2a squared b plus ab squared. And distributing a negative b, we get negative a squared b plus 2ab squared minus b cubed. Collecting like terms, we get minus 3a squared b plus 3ab squared minus b cubed. And we are done. Cool. Yeah, this is Basic Math by Lang. Yeah. I could show my book collection sometime. I would just have to do it like a proper YouTube video. It would just, I don't know. If I'm going to show my math collection, like that sounds like a real YouTube math video. Serge Lang has many great books. I think so. Yeah, I'm enjoying this so far. I'm trying to imagine and practice what would it be like to teach a middle school honors algebra course. Like, I think that an honors student in middle school would be ready for something like this. Okay, so I jumped to section 2 accidentally. Let's start from exercises from section 1. There's no exercises in section 1, but there's exercises in section 2. I think it's good so far. I mean, I'm brand new to it, so I don't have strong opinions yet, but I like it so far. So in section 1.2, we get rules for addition. And exercise 1 says justify each step A plus B plus C plus D equals A plus D plus B plus C. This is the true first exercise in this book. This is actually the first exercise. And like, no joke, this would be the first exercise in an Intro to Proofs course in college. Like, prove this. Like, we all believe that this is true, and we're so used to using this fact all the time. But what are actually the step-by-step individual reasons? What is the argument for why this must be true? Okay, so let's see it. This one is the part of the book where at least once in your life you should be writing out every single individual rewrite, I believe. And then as you get used to it and you've done it a few times, then you can skip steps and do a whole simplification in one step. But at least once in your life, I think that you should justify every single step. Okay. So we start with the left-hand side. I like to put a little question mark in my equal signs like this. This is non-standard notation, but it's perfectly fine to use your own shorthand in your own notes. So this is our claim or our question. So we begin with the left-hand side, and then we want to do a bunch of steps rewriting this many times until we get to the right-hand side. Like, we start from the left-hand side, and then we want to rewrite it until it matches the right-hand side. Okay, so let's see. This one's like a little tricky, I feel. Okay. So ultimately we want A plus D on the left. So this sort of stuff is kind of like a puzzle, I feel. A plus B. So since I want D on the left and C on the right, I'm going to begin with an application of commutativity of addition. So here we have commutativity. I will just write the steps for now, just like in small letters in a different color to the right of every step. Now, this is tricky. But at the moment, this is written in the form x plus y plus z if x is the bracketed a plus b, right? And we know that this is x plus y plus z by associativity. So we know that this is the same as a plus b, which all of, like, this is a bracketed thing that I call x plus d plus c. And now you can use square brackets or curly brackets, but whichever style you prefer, try to make your outermost ones bigger than the innermost ones so that you can see some nesting. Now, by associativity, we have this is the same as A plus B plus D. Plus C. Now, I can use commutativity and now I can use associativity and now I can use associativity again. And now this is in the form of the right-hand side. So getting like kind of careful about these associativity rewrites. Like associativity is kind of a pain to write every individual rewrite because it's like a little tricky, a little finicky, I feel, but it's worth it. You've never really read Lang's books. You read one on algebra. Algebra is hard. Yeah, I audited a course at UC Berkeley based on Lang's algebra, and it was, man, that book is hard. That one is really hard. It's always good to explicitly mention axiom, theorem, anything you used in that particular step. Yeah, I was saying it out loud, but if this is a solution set or my homework, if it's your homework, you shouldn't just say it out loud like as if you're lecturing, but I'll use ASOC instead of ass because people will giggle if I say ass. Associativity, commutativity, associativity, and associativity. Right? Nice. Okay, so that's the first exercise. There are several more of that form. Oops, this is the other yellow book. Yellow books are hard. In math, if you see a yellow book, you should be a little frightened. Yellow books are hard. So we have several more like of the same form. And then ultimately we get to the next one that's really, truly different is, number 11 does say show that minus a plus b plus c equals minus a plus minus b plus minus c. What does this ask us to show? Recall the definition of minus a. It is a number which can bring you back to zero. When you add this other number, you invert a to zero. So we want to show that the opposite or the inverse of okay. Let x be the additive inverse of a plus b plus c. Oh, no. How would I write this out? It suffices to show that a plus b plus c plus so to this effect, by repeatedly applying associativity and commutativity. Well, let's be careful about that one. Recall that in the text they say that a minus b is just shorthand for a plus negative b. So that is just shorthand. So we are here right now. And then by regrouping this is by commutativity and associativity. This is often called regrouping. Like, regrouping is repeatedly using associativity and commutativity to move the additions to other places. A minus A is 0 by definition. B minus B is 0. And C minus C is 0. And now 0 added to itself is 0. That's actually the definition of what 0 is. Yeah, Mumford's Red Book, Adams' Blue Book, Ravenel's Green Book. Yeah, absolutely. Red books are hard too. I would say too hard, like a warning sign. That's funny. Yeah, I'm just joking. I hope that Springer doesn't sue me for damages. That's obviously, I love the yellow books. Yellow books are excellent. They're the best, actually. Okay, so I don't know if this is my favorite proof of this. We could also have a plus b plus c plus negative a plus negative b plus negative c after working it, I kind of feel like this is a little nicer to remove one level of parentheses by associativity. And now all of these are additions. So now I can just say commutativity once. Because remember that addition satisfies commutativity, but writing something as a subtraction fails commutativity. Subtraction fails commutativity, but writing a subtraction as an addition satisfies commutativity. As long as you use additions everywhere, then you can rearrange additions. So I rearranged everything using additions. And now, on this step, the definition of minus a is the number which adds to a and equals 0. B plus negative b is 0. C plus negative c is 0. And now we get that this is 0. I think that that's a slightly nicer proof than relying on negatives, but both approaches kind of work. Watching your live from new tablet, cool. Congrats on your new tablet. What's up, Adar? How's it going? If you're asking what book I'm using Serge Lang's Basic Mathematics, and the idea for this is an intro to proofs. I want to be teaching an Intro to Proofs course based on Lang's Basic Math. Cool. So that was an exercise. I think I got it. Then we have an exercise like number 13, which says solve for x So solve for x in this equation. That's great. Can I ask a question? Yeah, absolutely. What's your question? I'm going to call this a solution because it's not really, I'm computing a specific solution rather than proving a general statement about all numbers. This exercise uses specific numbers. If negative 2 plus x equal 4, then we can add on the left a number. So 2 minus 2 plus x equals 6. And 0 plus x equals 6. Therefore, x is 6. No, that doesn't sound... No, I don't feel like working that problem. Thank you, though. If somebody else wants to try to work it, let's see. You've got xy minus x plus y equals 3, where x and y are integers. So if anybody wants to try to work that, be my guest. I mean, it's kind of similar to the math that I'm working from this book, but what have you tried? What have you tried so far? Okay, then we have prove the cancellation law for addition. What exercise number is this? 22. So we want to prove if a plus b equals a plus c, then b equals c. So this proof is using exactly the same idea that I just worked in the previous specific example, but we're going to be proving it for all numbers a and b and c. So let a, b, and c be numbers. And suppose a plus b equals a plus c. Then we can add, say, on the right by negative a, so we want, and I should justify that, I think. This is in the text, so there's a name for it, but this math fact is that if a equals b, then a plus c equals b plus c. You can add a number to both sides of the equation, because if the two numbers are equal, a and b, then they're just different names for the same number. Then a plus c is b plus c. I wonder if Lang proves that. So here on the left-hand side and the right-hand side, I added negative a. Then by using associativity or commutativity of addition, maybe. Associativity commutativity definition of negative numbers. Definition of zero. If I were super formal, we'd first do commutativity of addition and then definition of zero. Zero is the number that you can add to anything and it equals itself. B plus zero is equal to B. Right? Have a nice day ahead, everyone. See y'all. See you, dude. Great to see you, Levi. Thank you for tuning in. What do I have lined up for today? Do I want to do my lecture? I think I'll do it tomorrow. Today I'm just going to announce. I'm going to film my video announcing the course. I want to make sure I at least get that done. Okay, y'all. So I wonder, is anybody in the chat excited to follow along with me in a pure math course on basic mathematics for adults? Like, the idea is that this is for adults. This is your second time through, like coming back and relearning math and learning it the right way. And learning intro to proofs using high school material. I wonder if anybody's interested in following along with a course like that. So here's my scratch work. This is my notebook. If I wanted to send this as a solutions to students, I would typeset this and make it and use sentences and fill in some details. Even the basic mathematics would be above my level. You can't do this? You weren't able to do this one? Come on. It's just because I haven't done my lecture yet on the material that you need. So, and please, oh, you are interested, so please do teach. Nice. Awesome. I'm happy to hear that. Okay, tomorrow I'll film like a really cool first lecture, I think. But first I have to decide for this. For these recorded videos, do I wear a V-neck? Or do I try to pretend as if do I dress the part of a teacher and wear a button-down shirt all the time? Let's do it. I think we should wear a button-down shirt. No, I'm not leaving. No. We're going to film a YouTube video. We're going to film a proper YouTube video now. Which college? I graduated 14 years ago from Oklahoma State University in the U.S. What about you? Nice to meet you, Adar. Yeah, I'm coming back and relearning math for fun for myself. Why? No, you don't have to delete your message. No reason to delete messages. Yeah, some people like to delete their messages for some reason. Okay, so how do I want to do this? All right, when I'm filming a YouTube video, I'm not reading chat. I'll come back and I'll read chat once I'm done. And there should be no background music as well. Yeah, I think that there's not. Where do I want that guitar to sit when I'm doing my... I think that's all right. Do N8. What is N8? All right, that's the last time I'm reading chat for a second here. Oh, I've been recording this whole time. All right, let's record. Hey, what's up? I'm so excited. We're going to be kicking off a brand new series. We're going to run an actual proper course in basic mathematics. The idea for me is I have this idea that math can be a hobby, okay? Math can be a hobby. I know it can be because it's a hobby for me. I freaking love math. I graduated with a degree in pure math 14 years ago in 2012. Then I went and worked in the software industry. I worked at big companies like Apple and Google and some others. And I met a lot of people over the years, a lot of people who studied math for fun for themselves. I think that that's just such an underrepresented category of people. There's a lot of people out there studying math just as a hobby because it's beautiful, because it's fun. Some of the most famous mathematicians that we remember, one of them who comes to mind is Pierre Fermat, and he had a bunch of open questions for a long time, including one called Fermat's last theorem, which was considered just this beautiful result that was only proved in the 1990s. Anyways, what I'm trying to get at is that he was, I believe, a lawyer, certainly not a full-time mathematician. He studied math recreationally for fun, as a hobby, because it's beautiful and it's good for your brain. So I think too many people are scrolling TikTok and not enough people are studying math for fun. So we're going to run an introduction to pure mathematics and introduction to proofs for adults for fun, using this terrific book by Serge Lang. And yeah, I invite you all to join and work through this book with me. So if this is your first time here, I don't normally post videos like this too often. I typically do a daily live stream. And so we're actually literally live right now. I put away chat because they're too distracting at the moment. But I just run my daily practice sessions, relearning math and also trying to develop like a higher level of mastery of math. I know all the math that's in this book, but I am practicing still because I'm practicing how to teach this material. On the one side, that just sounds fun to me, man. Like, it just sounds really fun to be able to teach intro to proofs and all of the middle school and high school curriculum. I think I forgot to say that this is a high school book written in the style of a pure math book, which is really awesome. Like, that sounds fun. That just sounds really fun. Like, if I didn't have to make money, I might do that just purely for fun as a hobby. Like, work every single exercise in this book and teach it to people for fun. But then on top of that, I'm trying to pivot from a career in the software industry into teaching middle school or high school mathematics. And I have a theory that somebody could run an honors middle school algebra course out of this book. Like, I think that the United States curriculum just really does a disservice to students because we only show proofs in geometry. And we show this weird, watered down, formulaic version of proofs that uses a table, like this table method. And it makes sense historically why we would show proofs in geometry, because the most famous, most successful math book of all time is Euclid's Elements, which proved all of geometry from the ancient Greek times. And it was based in this axiomatic, formal system of math. But the thing that bothers me is that that book also included many other types of proofs of things that we would consider elementary math or middle school math, or high school math, depending. Like things like the fact that there are infinitely many primes, for example. That proof comes from Euclid. It's a beautiful proof. And real mathematicians who are inventing new math and proving the fact that some new truth is forever true in any universe, like we literally send out prime numbers into the galaxy, into the universe, using radio signals or something, I don't even know, to try to find extraterrestrial life. If there's intelligent life out there, we think that they would have discovered prime numbers, that any intelligent life would come to the discovery of prime numbers. Like, this idea of prime numbers exists in the world. It's not a human invention. It's a fundamental truth in the world. The process of discovering truths in math is something that is common to all math. It's not just something that you do in geometry. And I think many high school teachers are not even equipped to teach proof-based math. Most of us learn math in this pattern matching style where you see a bunch of examples, a bunch of worked examples, and then you follow the pattern. But you don't understand why the pattern works in the first place. For some people like myself, that's harder, actually, to just memorize a bunch of patterns and not understand why the pattern works. It feels very arbitrary, and then you get questions like, when am I ever going to use this in the real world? Like, I don't feel like memorizing all these various recipes if I don't want to, become an engineer, or like I struggle to see why we're solving with polynomials with a quadratic equation or something. And like the truth is that you're not going to ever get paid to solve something with a quadratic equation. Like maybe, but I know for sure I've never used a quadratic equation as a software engineer. But you use the mathematical reasoning behind the quadratic equation all the time. I think in every single industry. Like the creativity and the method of abstraction and problem solving skills, like general problem solving skills that's inherent in proofwriting, that you get paid for. That's what like earns you the big bucks. That's what gets you into Google or something. It's the reasons why things are true, like being able to make a concrete argument, showing high schoolers proofs, and showing high schoolers mathematical arguments. I like to just call them a mathematical argument, is directly relevant to the real world. Like somebody should teach basic propositional logic along with intro to proofs, I think. And then suddenly you have debates. You have like the method of debating one point versus another and logical fallacies, and you get all like you get argumentation in non-numeric settings. Like you get law. Like law is so similar. Like a legal case from an attorney is so similar to the axiomatic method that math proves or works in. You have definitions, you have connectives, like if this, then that. You have previous results of previous laws, and you try to combine two different laws and show how this example, this case is an example of these two different laws applied together or something. At least that's my understanding. I've never taken a single law class in my life, but I know that mathematics as a major is one of the best majors for an undergrad degree, pre-law. For a pre-law degree, math is one of the best majors that you can study. Yeah, and so I'm just super excited about this. We're going to work in stream. I'm going to do 1 week on middle school, high school fundamental math. Then I'll do a week of streams on college level math of calculus and linear algebra and maybe some others. And then I'm always structuring streams to have 1 week of graduate level math where I'm learning new math for myself for fun. For a while, we've been working representation theory, which is applying linear algebra to the mathematical study of symmetry. A very beautiful field that I'm learning live here on YouTube. So that's the structure. We're changing the stream structure to have more high school math, middle school, high school math, pre-calculus. We should just call this a pre-calc book. This is all math before calculus, I think is accurate. But it's done right. It's like done well. It's written in the style of a pure math book. I like it so far. I'm not too far into it, but so there's the practice sessions that are live. Then during these weeks where I'm working fundamentals, I'm going to be filming proper lectures without chat, filmed potentially privately, maybe live, but it's going to be a lecture on a section, and I'm going to try to follow a syllabus. I'm going to try to follow like a lesson plan, preparing for someday when I get a classroom of my own and I get to teach the little children pure mathematics. So I'm excited, and I invite you all to follow along with me. Get this book. It's terrific, by Serge Lang, Basic Mathematics. It's hard. I mean, it's a hard book, but like if you're the kind of person who likes to solve Sudokus for fun, or if you're the kind of person who like you didn't feel like you did well in math in high school and you want to like come back and conquer it later on as an adult, like dude, this is such a better hobby than scrolling TikTok. Like, get off of YouTube right now and go get this book and go work the first 2 exercises. They're actually harder than you might think, but all it is just addition. It's literally just addition. Let me show you. I can put this up to the camera, fair use and all that, right? Let me show you the first exercise set. Like, these are the very first problems for this book. And I think that somebody could teach an honors Algebra 1 course in middle school using this book. Dude. Those are the very first exercises. Justify each step using commutativity and associativity and proving the following identities. A plus B plus C plus D equals A plus D plus B plus C. Like, some people say, like, oh, math lost me when everything turned into letters. And I think that's a shame because we wait too long, in my opinion, until we start introducing letters, because that's where real math, that's what real math is in some sense. Like, showing that for any numbers, this pattern always works. And there's a concrete, clear argument why this fact always works. So I'm excited about this. We won't only be using this book, and I'm going to be jumping around like all over the place, which in the foreword of this book, Lang recommends that you jump around as a teacher, which is awesome. This is another thing where I think that the U.S. curriculum is... I can only speak to the U.S. because I have only ever lived in the U.S. and taken classes in the U.S. But it's probably the same in a lot of other countries, I think. But we go very depth first, and we teach students to work 30 exercises from, the quadratic equation or something. And then we do 30 more problems on something else about polynomials, or like completing the square to solve quadratic equations or something. I just think it's so much more valuable to jump around a bit. Why don't we show matrix addition immediately after addition? Like, you can add 2 numbers, a plus b, and a plus b equals b plus c. A plus b equals b plus a. Like, you can add 1 plus 2 is the same as 2 plus 1. Okay. Turns out that in math, you can also add blocks of numbers. 1, 2, 3, 4 in like a little grid, plus 5, 6, 7, 8. You add 1, like the top left numbers, and that's the new top left number. You can add the top right numbers, and that's the new top right number. You can add the bottom left, and then the bottom right. And this forms a new field of math called linear algebra. And it's just the very beginning of this really incredibly beautiful field of math, which turns out to be, speaking from experience as an engineer, the most useful math in the world right now. Like, this YouTube and recommendation algorithms, AI, is all built on matrices, like these blocks of numbers and treating them as objects in themselves. Why don't we introduce that immediately, like with addition? Is that kind of crazy? Is that crazy? I think it's a good idea, because then it takes a little bit more work, but you can define multiplication of two blocks of matrices, two blocks of numbers, and the regular numbers satisfy a times b equals b times a. Like 2 times 3 is the same as 3 times 2. Nothing too crazy right now. But blocks of numbers don't work that way. Block 1 times block 2 does not equal block 2 times block 1. Having examples from quote-unquote more advanced math or different math, different fields of math, and then contrasting that with a simpler math, I think that can be a really effective way to teach, at least for the right student. So I'm excited. Join me for this. Keep an eye out for lectures. I'm going to be posting these. This video is already longer than I planned. I should cut out something, but hey, it's live, so these things happen. Thank you for watching, and see you sometime in the streams. There's also going to be a paid group lessons option, and we'll figure it out as we go. I'll figure out how this is going to look, but I think it's going to be Zoom classes on Saturdays, ? So if you want to hang out with us in Zoom and work some problems and ask questions and meet fellow math hobbyists, there's your chance, dude. Like, we already have 3 people signed up so far, and it's turning out to be a really nice little group. So hope to see you there, and if not, feel free to follow the public free videos. I'm looking forward to this. Like, I'm genuinely, for myself, looking forward to working the exercises from this nice yellow book. So thanks for watching. All right, see you around. There we go. There's a little YouTube rant. What do you all think? I hope you solve your struggles. I will be great. You one day. What? Software engineers are being automated at lightning speeds. Yep. I didn't want to. Yep. Took me 23 years to understand that everything is built on maths. The whole world, kind of. Real math. Yeah, I'm ready to learn in this age. Are you teaching to a 6-year-old? Kind of. But like a motivated 6-year-old. Like somebody who wants to learn math the right way. Yeah, I think that you could teach a 6-year-old some of this stuff. Yeah, I mean, I have a tendency to kind of to talk down almost, but I hope it doesn't sound like I'm talking down to other people. I'm trying to find a common ground where we all know something like 2 times 3 is 3 times 2, but not everybody knows about matrices, right? So something I understood. I hope you understood what I just talked about just now. All right. Thanks, y'all. I had fun today. Take care. If there's no more questions, I'll see you around next time. Awesome. Okay. Thanks for watching, y'all. Bye. If you want to support me, there's a couple of options. I have a buy me a coffee. That's one option. If you just want to drop a tip, that's always appreciated, but never, ever expected. A free way is that I have a second channel, classical guitar. So you could follow my second channel. That also helps me grow my audience. Let's say. What else? Oh, join the Discord. Discord is chill. It's a community of hobbyists, of enthusiasts, deep hobbyists, people trying to better themselves with fulfilling, meaningful hobbies like math and classical guitar. That's also a way to find the Math Academy that we're building up. And email for one-on-one private tutoring or group tutoring on basic math textbook? Okay. Thanks for watching, everybody. Bye. Bye. Like and subscribe and share with all of the math nerds that you know. Thank you for watching.